So morning, everybody. Don't forget your name tags, please. They're always up here, so they're always up here. Okay, everybody, let's begin. I noticed that the class has thinned considerably. We started with 150 people in class, and today we have maybe 40, right? At this rate, in 2 weeks' time, the class will be empty. I didn't count. Don't let that happen. So we're going to continue with our series on training neural networks. So Chantal, what was the last topic we covered? I cannot hear you. Can you say that louder, please? Empirical risk minimization. Anybody else remember some of the topics we covered in the last class? Yes.
Backpropagation.
Sort of briefly, we haven't actually covered backpropagation. We just said that we spoke about gradient descent as a mechanism for training, for optimizing functions. But then we also explained how training a neural network is basically a problem of function optimization because why? Sergey? So why is training a neural network an instance of function optimization?
Because we have a cost we want to minimize, and like we need some of that.
And what is the cost a function of?
Function of the output and the desired output.
Anybody else?
Function of the parameters.
It's a function of the parameters of the network, right? And so we want to use gradient descent. Why is it a function of the parameters of the network and not the input?
It is also a function of
Is it?
the weights are the only thing you can change. Yeah.
Because the inputs, the training instances are given to you. Those are not things that you can vary. So the only thing that's left that you can vary are the parameters of the network. And so we have a situation here where you're given a training set of input-output pairs, but those are given. They can no longer be modified. So as a result, what we define the empirical risk, which we also called our loss, which is the average divergence between the output of the network and the desired output of the network at each of these training instances. And the hope is that if you minimize this, then you would match the correct output at each training instance, and somehow it's going to magically fit the entire function. So before we continue, we're going to cover a vast amount today. I will be fast. And if I'm too fast for you, then just let me know. So I'm going to introduce some notation because we're going to use symbols, and notation is important. We're assuming that the network is layered. And so the layer, the associated with any variable, is shown as this parenthesized superscript. And now, at any layer, any neuron has a bunch of incoming weights, and it has a bias. We saw that. So the bias is represented as the bias at the jth neuron in the kth layer is going to be b subscript j superscript k with the k in parentheses, right? And so also the set of all the weights coming in to the jth neuron of the kth layer are going to be wij, where I is the source neuron, j is the destination neuron, and the superscript is the layer. And now I'm going to represent the output of the ith neuron of the kth layer as yi superscript k. And just to make things consistent, the input, which has nothing to do with any neuron, I'm going to represent as the output of the 0th layer. So I just make it a superscript 0. This is just for notational consistency. And here's how we had our gradient descent algorithm defined. To minimize any function, such as loss of w with respect to the argument w, you would initialize the parameter, and then you would iteratively take a step in which direction? Opposite the gradient. And so why was it opposite the gradient, Alex? It's a direction, not the slope. It's a direction, right? The gradient is the direction in which the function increases fastest. So you want to take a step against the gradient. And now, when we are training neural networks, of course, our loss function is an average divergence. All the parameters are all the sets of weights and biases. And so the gradient we also know is, how did we define the gradient, Joseph? The partial derivatives, right? So the entries of the gradient are the partial derivatives. So that means that there's something wrong with this notation. What's wrong with that notation? Pardon me?
It's not partial.
Those are not partial, but these are supposed to be partial derivatives, right? And so they're not, it's not really partial derivatives, it gets a little more tangled, but so we're going to use this, the full derivative notation. But each parameter is going to be updated against the derivative of the loss with respect to the parameter. And this is the term that we actually need to be able to estimate for a complicated network in order for us to be able to perform these updates. Now, the loss is the average divergence over all of your training instances. And using the linearity of differentiation, the derivative of the loss with respect to any parameter is the average of the derivative of the divergences for the individual training instances. And therefore, the term that we will need to compute is this derivative of the divergence with respect to the parameters. This is the key bit. Once we know how to compute it, we know how to perform gradient descent and how to train the network. Now, we had some, I'm going to do a quick recap of derivatives, right? For any differentiable function, assuming that inputs are scalar, how did we define the derivative, CEO?
So we define it as the vector composed of all the.
No, I'm scalar. A function, was it a vector? Okay, assume that the inputs are scalar and the functions are scalar. How do you define?
So it's the derivative.
Yeah.
The scalar against the scalar.
Yeah. So how did we define it? What was it?
Oh, so it's like the change of the output given minor turbulence in terms of the.
Is that how we define it? James, do you know all the answers? So okay, how did we define the derivative?
The derivative is the rate of change of.
Is that how we defined it? Anybody else? Aditi, how did we define it?
Change in X.
Heavens.
It's the alpha, the factor by.
It's the factor by which you multiply the perturbation and the input to get the corresponding perturbation of the output. This you have to remember, okay? So the rate of change, etc., are just outcomes of this particular definition. And so, thank you, Zakel. So that's what you have. For any delta x, the derivative, yes.
To me, when you said that, it sounded the exact same as when CU said that. So, like, what's the difference in what you're looking for there?
So no, I'm looking at it as, did she say exactly that?
Well, she said you changed this a small amount, and the output a small amount, and to me, you're saying there's a factor.
It's a factor. Changing the input changes the output. That's a known fact, right?
But that's the factor that's describing the same thing. There's a factor you change it, like, but I don't understand what the difference is there.
The difference is that you're thinking in terms of the multiplicative factor that multiplies delta x to get delta y, and you'll see why this distinction is important, right? So I'm going to introduce something called a influence diagram for this. If I have a function y, y being a function of x influences y. So I have an arrow from x to y, right? So the corresponding derivative equivalent is the same relationship, but now the edge is going to carry a weight, which is the derivative of the output with respect to the input. And so if the perturbation at the input to this edge is delta x, then the output is going to be the edge times delta x. This clear to everyone? Right? We're going to use this. So now, suppose I have a differentiable function of this kind. Going back to your answer, all right? Over here, how would you define the derivative over here?
Using your same language there, it's a vector, so it's a factor for each x. There's some relationship where you multiply the result of the perturbation with a linear scalar.
Is that how we define it? So how did we define the derivative in this case? You've been here for 3 lectures. So yes.
It's like the gradient transposes the gradient.
You're giving me you're describing it. But how did we define the derivative? Did we change the definition of the derivative between the vector case and the scalar case? So what was the definition? You're giving me a description again, right? What was the term? It was once again the factor that multiplied a perturbation of the input. Eric, if you're not looking at class lectures, please shut the laptop, right? Yes, sir. Thank you. Okay, fine. So it's a factor that multiplies the per small perturbation in the input to give you a perturbation in the output. So this should not be a question that I should look at blank faces for when I ask you, right? Now here is, okay, I've given you the answer. How would I represent the influences over here? There are n variables going in. Each one of them influences the output, correct? That's going to be my influence diagram. How do you think I would draw the derivative version of this diagram? I'm going to have the same thing, but every edge is going to have the partial derivative of that variable, of the output with respect to the input variable. Now, the difference between a partial derivative and a full derivative is this. There's just one connection from x to y, right? There's only a single path, which means that perturbing x is going to perturb y, period. Here we will generally use the full derivative. On the other hand, when you have many influences coming in, I can fix many and perturb one. So these are going to be partial derivatives. And then here is the rule that we will have, right? If you look at the total delta y, the delta y is going to be the cumulative perturbation from all the inputs. Just using the notation of graphs, you're going to get delta y is going to be the sum of the perturbations from every incoming line. And so that's going to be the sum over all of the inputs of the partial derivative times delta x. Right? This making sense? So now suppose I have a nested function of this kind. F of g of y equals f of g of x. Then here's the influence diagram. X influences g, influences y, right? So how do you think I would write the partial derivative, the derivative equivalent of these influences? So that's going to be like so, right? Delta x, so the first edge is going to have the derivative of g with respect to x. The second one is going to have the change derivative of y with respect to g. And now if you look at this going through, you will see that delta y equals delta g times dy over dg, right? But delta g is delta x times dg over dx. So if you change them up, delta y is dy over dg times dg over dx. So this gives you the derivative of y with respect to x, which gives you, what is this rule? The chain rule, right? We can see how this comes out. Now, suppose I have a function. Y is a function of many variables, but each of those variables in turn is a function of a common variable x. What is this going to look like, the influence picture? Yeah? Fan out and come back in, right? X is going to influence every one of these g's, and then each of these g's is, so the ith output I'm representing as zi, and then each of those in turn is going to represent the y, right? So now, Adnan, what would the derivative line be? So what is the figure going to look like? Evan. So what's the figure going to look like? Pardon me? It's going to look like this, right? Every edge is going to just have the partial derivative or the full derivative of the output variable with respect to the input variable. Make sense? And now what will the derivative rule look like? Nate, you want to take a guess?
So you're talking about how the perturbation in x then is going to influence g z of x.
I'm asking how does the perturbation in x result perturb y?
Through g of x.
All of the g of x's, right? So what is the equation going to look like?
Should be a summation, right?
Yes, because y gets the combined influences from what happened? Y gets the combined influences from all of the z's. So delta y is the summation over all the z's of the derivative of y with respect to z times delta z, right? And each of the z's in turn is delta z is this derivative times delta x. Put them all together, you get the distributed chain rule. Right? Very easy. And so for now, so basically we end up with this nested function. If I say I have f is a function of many z's, where z is some function g of x, then the derivative of z of the output L with respect to x is just this distributed chain rule, just repeating myself. Now let's go back up to our problem for today. How do I compute the derivative of the divergence? Any questions? No, right? So how do I compute the derivative of the divergence with respect to a single data instance? So guys, it's very likely that I'm not going to finish today's class. I have the choice of speaking very fast or speaking at a normal pace, but then I do need to finish this lecture today, so I can take up 40 minutes off over Zoom later in the day and complete this over Zoom, right? Oh, yes. Before I complete, is Laura online? So we have a person from the Eberly Center. We've been working with the Eberly Center from the last class. Is she there?
Not yet.
Can you double check?
Yep.
So when she comes on, so at some point when she comes on, the rest of the staff are going to go out and she's going to make a brief presentation to you, right? So again, I would prefer to do the 40 minutes later in the day. Would 5 p.m. work for you? No. So what would be a reasonable time? 6 p.m.? Oh my good God. Huh? Pardon me?
We need to record it.
We will record it, but the point is you might want to be online too, right? So it's on Zoom. 7 p.m. 7 p.m. Okay, 7 p.m. it is. You're going to have to try to make it, right? Otherwise, we will record it. Yes. No, I'm going to do this over Zoom, right? Yeah. It's the same. The Zoom link is on the class page, right? So this saves me the trouble of running through my lectures. Okay. So anyway, let me know when Laura is online. So how do we compute this derivative? Let's go back here, right? But first, there's a poll. Yes, there is a poll. Okay, you have 10 seconds, guys. You don't see the second poll? Yeah. All right, okay, so well, that saves us the trouble. Anybody want to answer this? Okay, can't see the second poll, that's bad. Okay. Can anybody want to answer the first question? What is it? True. And the second one? Which of the following two are true? First one, both of them are true, correct? So we just went through that. So, all right, just to drive the point home. Now let's go back and let's look at how we can compute derivatives. I'm going to show you this as an example. I'm going to use this tiny network, which has several layers of 2 neurons each. This is just illustrative. Now, when each neuron actually consists of 2 operations, as we know, right? First, you compute an affine function of the inputs, then you put it through an activation. So if I expand it out, that's what it looks like. And computing an affine function is the same as computing a linear function when I extend the input with a single one. So that's just to make it explicit. And here are all the variables again. The weights coming in to each layer are subscripted by the input and output neurons and superscripted by the layer. So the first one over here is going to represent the bias, okay? Now, let's note down all the other variables. I'm going to use this variable z. Z is the affine value that you compute at each neuron. At each neuron, there's a two-step process. First, you compute an affine function of the inputs. That's going to be the z at that input, at that neuron, which you put through an activation, and then you're going to get an output y. And once again, the z's are subscripted by the neuron index and superscripted by the layer, both the z's and the y's, right? And the final network output, I'm going to represent by the uppercase y, which is the output of the final layer. There's a desired output d, and there's a divergence function, which I'm representing as div. And our problem is to find out what is the derivative of this divergence with, say, this weight out here, the weight in the first layer. So again, we know that when we are computing a derivative, the derivative depends on where you're computing the derivative. It's not a global property, right? Which means for any given input, you need to know where the function is. And that means we're going to know what all the intermediate values are, what all the z's and all the y's are, which are dependent on the input. In order to compute the derivative, you need to know all of these locations, right, on all of these values. So as a first step, we're going to compute all of these z's and y's in what we will call the forward pass. So here, you're going to be given an input. You're going to pass it through the network. You compute all the intermediate variables and the output. And once you compute the output, you know where you're computing the divergence and what the derivative must be. And then and that is what we will compute. First, let's look at how we compute the forward pass. There's some inconsistency of notation, which I should fix. The 0 is what I'm using for the bias, okay? So anyway, so now let's start at the very input. Let's say I've given you an input. I've also got this extra 1 just to handle the bias. Now, what is the affine value that I would compute at the very first neuron? The affine value is going to be the weighted sum of all of the inputs, right? So it's going to be the sum over all of the inputs of wi1, because this is the first neuron. Superscript 1 represents the layer, times yi0. So the ith input is multiplying the wi1 with the weight that comes from the ith input to the neuron. And then you're summing this over all of the neurons. It's a very simple equation. So I can use the same rule to compute the z values in all of these locations. And so now I'm going to have the affine values at all of the neurons. Okay, is Laura on? Yeah. So ask her when she's. Laura, can you say something? Okay. Paul? We need your help. We have someone from Eberly.
What's her name?
Oh, I think she's just dropping it.
Oh, she's dropped again?
Okay, I will chat with her and let you know.
All right, so we're having troubles. Anyway, so we can compute these z's for all of the neurons. And then what would the next step be? Pardon me? Apply the activations to every one of these guys, and I'm going to compute the y's at every one of these neurons. The formula is very simple. You just apply the activation element-wise. And then the next step, what would I be computing next? Anybody want to answer me? So you over there, you guys, what would the next step be? Over here. Summing up what? Ryan? Yeah. So I'm going to be computing the affine values at all of the neurons again, right? It's going to be just the same weighted sum. Yes. So we're going to be computing the weighted sum of the outputs of the first layer neurons at each neuron, and you get the z values at each of the second layer neurons. And then you put them through the activations again. And you can keep doing this going all the way forward. Eventually, you're going to get the outputs of the final layer, and those are your network outputs. So in terms of computing the outputs, if you look at it algorithmically, it's very straightforward. I'm just setting my input y0, the 0th layer, as the input. And then subsequently, you sort of scroll through the layers, At each layer, you go through all of the neurons. And so you go through the layers, K. At each layer, you go through all of the neurons, which are indexed by J. For each neuron, you compute the affine value, which is just a weighted sum of the outputs of the previous layer. And then you compute the output, which just passes this affine value Z through the activation. And eventually, you have the output of the entire network. And so if I were to write it as pseudocode, this is what it's going to look like. In the first step, I set my 0th layer to the inputs. I've added this extra term over here just to handle the bias for notational simplicity. And then you go through the layers. Within each layer, you go through all of the neurons. The layers may have different widths. And for each neuron, you're going to compute the Z value. And then you're going to pass the Z value through the activation to get the corresponding Y value. The output of the network itself is the output of the final layer, right? Now, so we've computed all of these intermediate values going forward to the end. Now we must compute derivatives, right? And we're going to have to remember all of these intermediate values to compute derivatives because they are going to be because that's where you're going to be computing these derivatives. They're stored. Now, the first step in computing the derivative of the divergence with respect to the parameters is to compute the divergence itself, right? So first, you would compute the output of the network. You have the desired output. From those, you compute the divergence. Then the way you would actually compute the derivatives is this, like so. From this divergence, you would compute the derivative of the divergence with respect to the output of the network. Then you're going to take a step back from there and compute the derivative of the divergence. So remember, derivatives are always about how much does this function change for a small perturbation of the input, right? So if you want to do that, the way you would have to do it is to say how much does the perturbation of this guy change the output, right? But then the next thing is how much does the perturbation of this guy perturb this guy? And then you can chain it up. Then you take a step back and say how much does the perturbation of this guy perturb this much, this term, and then you've already computed how much perturbing that is going to change the output. And that's why you have to take a step backward. You cannot go forward. You're basically chaining perturbations, right? That's how different derivatives are defined. And so you would first compute the derivative of the divergence with respect to the output y, which will tell you how much a small perturbation in y will change the derivative. Then you take a step back and compute how much a small perturbation in z over here is going to change the divergence, because a perturbation in z will perturb y, which will perturb the divergence, right? Then you take a step back and say how much does a small perturbation in all of these parameters, which are going into the final layer of the network, perturb the divergence. Again, you're chaining perturbations, right? And then you take a step back and compute the derivative with respect to of the divergence with respect to the outputs of the penultimate layer, the second to last layer. Again, because you're chaining perturbations, right? The chain rule is going to get repeatedly applied. You always have to think of it in terms of derivatives representing how much a small perturbation of the value changes the output. And the way you would do it is how much does perturbing this guy perturb this one, and how much does perturbing this guy change the output. You keep chaining these things. And so you're going to keep computing your derivatives going backwards all the way to the parameters of the first layer. In fact, we can even compute the derivatives of the divergence with respect to the input itself, just taking this process one step backwards. And the reason we call this back propagation or error back propagation is that you're starting from there and the computation of the derivatives is going backwards. Okay, all right. So we have Laura online. Paul, what happened for the longest time is we would like to try to get an idea of how your background coming in affects your final grade. So we will actually be posting a survey later asking each of you to answer some questions about your background coming in. This will help us sort of figure out what we are doing right and what additional things we must have done to maximize your chance of getting an A, right? Basically learning the subject. A's don't matter, learning the subject does. Anyway, so continuing with the lecture, we're going to go back and look at, this was one of the reasons why we're going to have to extend the lecture. Let's look at how we would compute derivatives. So The first thing is we assumed that the divergence function was differentiable, right? And we have not specified the divergence function over here. I'm treating it as generic. We looked at a couple of different divergence functions earlier in the previous lecture. Anybody remember? So someone want to remind me of one of the divergence functions we considered, Thomas? The crossing. Did we speak about the entropy loss in class? The KL divergence, right? And can you mention some other divergence that we spoke of? The L2 divergence, right? So, and we assume that we have the formulae for those derivatives. So which means we assume that we actually have the derivative of the divergence with respect to all the network outputs. Now, I want to take a step back, right? If I take a step back, how would I chain it? I'm going to use the chain rule. If I have f of L equals f of y, where y equals g of z, then the derivative of L with respect to z is the derivative of L with respect to y times the derivative of y with respect to z. Here, what are the equivalents in our network? For this chain rule, what are the equivalent variables? Yes.
L is the loss, G is the hidden layer perhaps, and Z is maybe the input.
So here, L is going to be the loss. For the first step, G is going to be your divergence, right? L is going to be a loss, and G is going to be the activation over here, and then you have the Z. So applying this rule, the derivative of the divergence with respect to Z is the derivative of the divergence with respect to Y times the derivative of Y with respect to Z, right? Out here. Now this first term, we assume we already have. This second term over here, which is the derivative of Y with respect to Z for each of the neurons, that's just the derivative of the activation function for each of the neurons, right? And that derivative must be computed at the current value of Z. And we have already obtained Z during the forward pass. Yeah.
Is it the reason why we save those values?
Yes, we need them because we need to compute these derivatives, right? And so this is computed in the forward pass, and so I can write the derivative of the divergence with respect to Z. Easy, right? The next thing, what was the next thing we computed? Going back, Jessica. So, but that's already there. We've already got the derivative of the divergence with respect to the affine value Z, right? So does anybody want to give me? Yes? You there? I saw you raise your hand. I know you didn't mean it, but can you answer the question? Yes. Yes, what is the next derivative you would be computing?
The derivative of the divergence with respect to the final output.
That's, we already got the final output. We got the derivative with respect to Z. What is the next derivative you're computing? We're going back, right? So what would it be?
Derivative of Z with respect to the previous layers.
So anyone else want to help me? Help her? You want to compute the derivative of the divergence with respect to the weights, right? Which is these guys. And so the derivative, now observe that any single weight influences just a single Z, right? So this is no longer a distributed derivative chain rule. So the derivative of the divergence with respect to this W for the highlighted connection is going to be the derivative of the divergence with respect to Z, the Z that weight connects to, times the derivative of the Z with respect to the weight, right? And this first term, we've just computed, going backwards. What is the derivative of Z with respect to the weight? Anybody want to answer me? Janice? Some of you don't have names, so I'm going to call you by position, right? So, but anyway, so what would the derivative of Z with respect to the weight be? Who was it who said it? Okay, you, yes. Yes. Why is that? It's affine, right? Z is going to be this W times this input plus other terms, right? So the derivative of Z with respect to this W is simply going to be the Y. So the derivative of a Z with respect to a weight is going to be the input to the connection. And so if you write the whole thing down, and the input to the connection was computed in the forward pass. If you write the whole thing down, the derivative of the divergence with respect to a weight is the derivative of the divergence with respect to the z times the input to the connection. So the weight is connecting an input to an output. The derivative of the divergence with respect to the weight is the input to the connection times the derivative of the divergence with respect to the output of the connection, right? So now maybe you guys can answer my next question. Janice, what is the next thing I'm going to compute? The next? Okay, you guys, positions 2 and 3, what would I compute? And you need your name tags, yeah. Exactly. Hiding in the back row doesn't hide you from me. I'm just warning you. I will come to you, right? So pay attention. Now, the derivative of, so we can compute the derivative of the divergence with respect to all of these weights. And next thing, we're going to compute the derivative of the divergence with respect to these y's, right? And now for these y's, I can draw the influence diagram like so. For any given y, which is the output of the, what happened? Yeah. For any given y, something strange. What just happened? I don't see it here. Okay. So I can draw an influence diagram like so. So there are many neurons, but if you consider any y, y influences all of these z's, and z influences the divergence through various variables, right? Z influences things downstream, but eventually it influences the divergence, correct? And so the derivative that I would actually have to use is, the rule that I would have to use is this guy, correct? And so what will that give me? The derivative of the divergence with respect to y is going to be the sum over all of these guys, right? Of the derivative of the divergence with respect to z times the derivative of z with respect to y. It just follows from this rule, right? And so I can say that the derivative of the divergence with respect to the first y is going to be the sum over all of these z's that the y connects to of the derivative of the divergence with respect to z times the derivative of the z with respect to y, right? Are there any terms that we've already computed? Going back here, Janice, what are the terms here that we've already computed? Can you speak up loudly, please? Yes. So in this equation, what are the terms we've already computed? Pardon me?
The derivative before,
So which ones are those?
and the divergence and the previous layer.
So, but in that equation over there, which terms have been computed? Oh, you can't see this? I have no idea.
Sometimes it just comes up, sometimes.
Yeah, that's a Zoom thing. So what terms have we computed? Yes.
We just talked about computing e to y bit earlier.
So this one, so yeah. So this term has been computed, right? What is the next term we need to compute? Back to you, Janice. And what is that? What is dz dy? The weight, right? Because we know z is w times y plus some other additional terms. So the derivative of z with respect to y is going to be the weight of the connection of z with respect to y. So I can just replace that term over here. And so I've got the derivative of the divergence with respect to y being the sum over all the z's of the derivative of the divergence with respect to z times the weight, right? The weight from that y to the z. And I can use this to compute the derivatives for all of these y's. Everybody with me so far? Right? So if I come back to you for the next one, you're going to be able to answer me? Right? I see someone nodding their head sideways. So, so maybe Shikhar, you can answer. What was the next thing I would compute? What is that? Which variable?
The
Biases. I've already done that, right? I've got the derivatives with respect to the y's. So what is the next thing I'm computing?
For the previous layer, so the y I n minus 1.
But I already got that. That's what I have, right? So what is the next thing I would compute?
The derivatives for the activation for that layer.
Somebody else want to help him? Noel? Spandan, what would it be? We've already done that, right? Yes.
The prior C,
You're going to compute the derivatives for the prior z, right? Guys, you are zoning out, sitting back here. So I'm going to stay here. I'll let the guys in front zone out. Okay. Okay. So this is what we would be computing the derivatives with respect to z, which is simply going to be the derivative with respect to of the divergence with respect to y times what, Spandan? It's on the slide. It's going to be the derivative of the activation that connects z to y, correct? Okay. And what would be the next thing I compute going back, Arjun?
Look at the derivative of y, so you would basically multiply it by the weights of the previous layer, n minus 2.
So, but what is the next derivative I'm going to be computing?
The z is with respect to the y.
Going back, you're going to be computing the derivative of the divergence with respect to the parameters of that layer, correct? And for which we already know the equation. As the derivative with respect to any weight over here is going to be the input to the connection times the derivative with respect to the output to the connection, right? So I can use that to compute all these derivatives. And what next, Arjun?
We basically know the n minus 2, the derivative from there already. That's the weight. So you go back one layer to the z n minus 2.
I would be computing the derivatives with respect to y of n minus 2, right? And each y is simply the weighted sum of the derivatives with respect to the z's at the next layer, right? And then once I have that, I can go back and compute the derivatives with respect to the z's at the layer and work my way backwards all the way to the beginning until I compute the derivatives for the first layer, right? But I could also compute the derivatives with respect to the input. Right. So everybody clear here?
Do we stop at the weights or the input?
If you want to figure out how perturbing the input changes the output, then you would do the inputs, otherwise you wouldn't, right? There are problems where you do need to know that. Okay. So here is the overall, I'm not sure why that thing is there at the bottom right, but here's the overall pseudocode. You're going to start off by computing the derivatives of the divergence with respect to the output of the network. Take a step back and compute the derivatives of the divergence with respect to these z's, and then keep working backwards. First, you would compute the derivative with respect to these y's, which is simply a weighted sum of the derivatives for these z's. Then you would take a step back and compute the derivatives for these z's, which you get by the simple application of the chain rule, right? And then somewhere in between, you also compute the derivatives with respect to these weights, where for any weight, the derivative is going to be the input to the weight times the derivative of the output of the weight, the derivative of the divergence with respect to the output of the connection, right? So it's a simple formula. I can write it out in pseudocode like so. Now, here's what we're doing. These are the derivatives for the output layer. Then we're going back through the layers. And while going back through the layers, we are going back through the neurons. And at each neuron, we are computing the derivative with respect to the output of the neuron, which is a weighted sum of the derivatives of the affine values at the next layer. And then you're computing the derivative with respect to the input, the affine input to the neuron. And off the side, you're also computing the derivative with respect to the weights. Does anybody see the analogy between this code and what you do in the forward pass? It's actually very analogous, right? So just to help you see why this is the case, let me use a dot notation. So when I put a dot on top, it means it's the derivative of the divergence with respect to that variable, okay? And look at what's happening. The derivative with respect to the output of the neuron is the weighted sum of the derivatives at the affine values to the next layer, right? And then the derivative with the input to the neuron is simply going to be the derivative of the output times the activation. So this is very similar to what you're doing in the forward pass. In the forward pass, first you compute a weighted sum of all of the outputs of the previous layer, then you apply an activation, right? Here, you're computing a weighted sum of the derivatives at the input to the next layer, and then you're passing it back through the activation. So in fact, you could use the same code with appropriate change of variables going forward and backwards. Right? There's a second pole. We've taken a lot of time getting here. This is an easy one, so I'm going to give you only 15 more seconds. Stop, okay? So anybody want to answer this question? What was it? C, right? Backpropagation is not the process of training the network. Backpropagation is not used to update model parameters. Backpropagation is simply the mechanism used to compute the derivatives of divergences with respect to network parameters. Once you compute those derivatives, you can go plug them into gradient descent or any other form of update rule, right? Backprop is not a training algorithm. It's a derivative computation algorithm, okay? Now going on. So there are some special cases. I've assumed that the computation of the output of one neuron doesn't influence the output of other neurons. But then we saw some kinds of activations where it did. What was that? We generally call them vector activations, right? So in the case of vector activations, softmax was just one instance, Ruchita. So in general, you can have other vector activations where if I change the Z, it's going to change all of the output Ys. And this has a special significance to us. Now consider this case. If I change a specific weight over here that's going into this Z, is it going to change all of the Ys on the left-hand side? No, right? But on the right, on the figure to the right, if I change a particular weight, it's going to change one Z, but it's going to end up changing all the Ys, right? And so how do you think it's going to change our chain rule? Anyone? How would this change our chain rule? Anybody want to guess? James, you know everything, so you should.
I don't understand the difference though between these two, because every weight is connected to every output.
No, so a single weight and every input is connected to every output,
Yeah,
but this weight connects only to the Z.
But same with this now. One
Yes.
weight only connects to one Z.
Yes, but okay, focus on the Z's. How is this going to change this chain rule? Yes. Vectorize? No, is that it? Doesn't really change. Okay, how did we write the derivative of the divergence with respect to Z? How did we write the derivative of the divergence with respect to a particular Z? How did we do that? What was the formula? Somebody. It was the derivative, it's f prime of Zi times the derivative of the divergence with respect to Yi, right? This is what we wrote. Will this still hold? Why will it not hold? Why will it not hold? Yes.
It affects the other YIs that.
Yeah, exactly, right? So what we had over here was, in this case, we had Z influenced a single y, which influenced the divergence, correct? Here, any zi influences all the y's, right? And they all influence the divergence. So how is this going to change? You're going to have, so again, this is the vector activation, remember? And when we spoke of vector activations, for the scalar activation, this was the rule that we had. In the case of the vector activations, changing a z influences all the y's, and all the y's influence the divergence. So now to compute the derivative of the divergence with respect to any z, we're going to sum over all of the y's. And what would you sum? The product of the derivative of the divergence with respect to y times the derivative of y with respect to z. Make sense to everyone? Right? And so this is one special instance of this is the softmax, right? And in the case of the softmax, we have to use so the softmax we saw was yi equals e raised to zi divided by j summation e raised to zj, right? So I have all of these z's, z1, z2, z3, and you have the y1, y2, y3, and so on. But each z also influences every other y, correct? Now over here, what is the derivative of yi with respect to zi, the same guy? If I consider just a direct line, then I can write this term as yi equals e raised to zi times 1 over summation j e raised to zj, correct? Right? Is this first term a function of zi? What about the second one? It is also there in the denominator. One of those j's in the denominator is the zi, right? So if I compute the derivative, what is the rule I would apply? Is this the chain rule? You're going to use the product rule, correct? Can somebody give me the product rule for this one? Who wants to be the person giving me the product rule? Sanjana.
So you keep one constant, e power.
Give me the formula, give me the answer. Pardon me?
E power zi.
E raised to zi. And this guy doesn't change because the first time you're only taking the derivative with respect to the first term, right? And then what do I get next?
And then you keep e raised to zi constant plus and the derivative of
So what is that? What is the derivative of that with respect to e raised to zi?
only zi, then it will be minus
Minus
e power
e raised to zi times summation j e raised to zj whole squared, correct? Just writing it down, right? And so this you will observe is simply the square of this first term, right? And so you're going to get that the derivative of yj with respect to zi is, if I equals j, it's just going to be zi times yi times 1 minus yi, right? And if I was taking the derivative of yi with respect to some z which was not zi, then this first term would not happen, right? Because this first term is not a function of that z. And so all you're going to be left with is the second term, and so you're going to get minus of yi yj, okay? You can work it out, but you get the idea, right? And you will observe over here that the first derivative is always, is it positive? For the direct line, is this derivative positive or negative? If I'm computing the derivative of this guy with respect to this, is that derivative positive or negative? Positive. It's always positive. It's yi times 1 minus yi is between 0 and 1, right? What does it tell me in terms of whether I should be increasing z or decreasing z? So you're always going to be, so you're going to be increasing things. The derivative is positive, right? So if I want to increase is it positive? Yeah, it's positive, yeah. I got myself confused, but you get the idea. The derivatives of the two are going to be opposite. So one of them has got to decrease, the other's got to increase, okay? But anyway, getting this back, you can see the point is that when I have a scalar vector activation, you actually have to sum over all of the outputs, right? And so the simple chain rule that we had up there, that changed to the distributed chain rule for vector activations. And correspondingly, your pseudocode over here is also going to have to change. At each layer, you would have to use the corresponding rule. If you have scalar activations, you can just use the simple chain rule. If you have vector activations, you're going to have to use the vector chain rule, right? Anyone with me? Everybody with me? Anyone with cover? Any doubts? On Zoom, any questions? No, okay. So let's look at, so the vector activation was one special case, right? Now we can also look at other kinds of special cases for that influence how we compute derivatives. And some of these will appear in the quiz. I'm going to go over only one or two in class. The first is the ReLU, and the second is the max. Now what is the problem with the ReLU? Is it non-continuous? It's non-differentiable at the juncture, right? So now suppose the input is exactly 0. What derivative would you use in the gradient descent rule? We don't know. There is no derivative defined, right? What about the max? Is the max differentiable everywhere? Is it differentiable? How many people say no? Raise your hands if you say no. Raise your hands if you say yes. If you haven't raised your hand, raise your hands. Right? That's shameful. So let's go through this again, right? How many of you think it's differentiable? Raise your hands. How many of you think it's not differentiable? Raise your hands. I expect to see the entire class one way or the other, right? Otherwise, you're not paying attention. Okay, so why do you think it's not differentiable? Anyone? Here's the thing. If you think of it in terms of measures, both of these functions are differentiable everywhere except at one point, right? Or a small set of points. If you take the measure of the set of points where the function is not differentiable, it's exactly equal to 0. So in a measure theoretic sense, these are actually differentiable. It's kind of crazy. But there is one point in the case of the ReLU where the function is not differentiable. When the input is negative, what is the derivative for the ReLU? When the input is positive, what is it? 1, right? So, but at 0, it's not differentiable. And for these things, we use something called subgradients. There's a lot of math and gunk about subgradients. Here's how you define subgradients. I won't actually get into it, but remember we said delta y equals alpha delta x, and we use this term alpha in your gradient descent rule. That is the direction of steepest ascent, right? When a function is not differentiable at a point, but is continuous, then you change this, then you can use a different definition. You say delta y is greater than or equal to alpha delta x. And any alpha that satisfies this property can be used in the gradient descent rule, because you know that walking in the direction of that alpha is going to increase the function. So going against that alpha is going to decrease the function, right? And so if you actually draw these hyperplanes that are normal to alpha, you'll find that they're always below the function. They're called subgradients. And when you use, so here, for example, the blue function is a curve. At that corner, it's not differentiable. I can draw a whole bunch of red lines touching the function at that point, which are entirely below the curve. The slope of any one of these lines can be used in my gradient descent rule, and they're all subgradients. Right? So there's a little more to it than that, but you get the idea, right? And the reason for that is that you want to step in a direction where stepping in the direction is going to, what do you want the step to do? it's going to decrease the function. And so if I find an alpha which satisfies this property, I can use that alpha, right? If the function is differentiable, then the gradient is uniquely defined. Otherwise, you're going to use something of this kind. But then for our purpose, there's a slightly different way to look at it, right? Think of the ReLU. The ReLU is, do we have an eraser here somewhere? I guess not. Okay. So I'm going to try to draw here. The ReLU is a function of this kind, right? Now over here, you can think of that as a hinge where the line is coming straight through, the function's coming straight through, and then turning rapidly to get a slope of, what is the final slope? 1, right? And so you can think of the function as instantaneously rotating from this to this to this to this. You're sort of rotating, right? Instantly. And so every one of these slopes is a valid slope at that point because the function is rotating, right? You can think of it as a function that's rotating at that hinge. And so you could use the derivatives of any one of these guys in your gradient descent rule. So here, for example, alternately stated, if I were to plot the derivative of the ReLU with respect to the input, then for negative inputs, the derivative is 0. For positive inputs, the derivative is 1. Was there a question on Zoom? Someone forgot to mute. Okay. So for negative inputs, the derivative is 0. For positive inputs, the derivative is 1. What is that range between 0 and 1? That's the range of slopes that the function takes as it rotates from a slope of 0 to a slope of 1, right? So any derivative in that small vertical range between 0 and 1 can be used for the junction, right? So now, something like that. Oh, I tried to make it stop at 45, but it wouldn't. So you can't use anything beyond 45, but you get the idea, right? Here's the other thing. The max is also a special case of a ReLU, really. Why is the max a ReLU? Suppose I consider max of x1, x2, right? If I consider max of x1, x2 as a function of x1, then this is x1. This is the function, right? And so long as, and let's say this is x2, so long as the function is below x2, the output is going to remain x2, right? So that would be this. And then the moment x1 goes greater than x2, it's going to take the value of x1. So it's basically a ReLU shifted upwards, right? And so what does that tell me? The derivative is going to be 0 with respect to any variable until it hits the value of the current highest variable, right? After that, the slope is going to become 1, right? And so, but there's a different way of thinking about it too, right? Suppose I have a collection of inputs and I'm picking the largest one. So I have x1, x2, and x3, and let's say x3 is the largest one currently, right? Will perturbing x1 perturb the output? No, because x1 is not the largest. Will perturbing x2 perturb the output? Also no. So what is the derivative of the output with respect to x1 or x2? 0. Will perturbing x3 perturb the output? It will. So what would that derivative be? 1. Except when both x3 and x2 are the same, right? In that case, for both x3 and x2, you can use any value between 0 and 1. That clear to everybody? Right? So, yes. I have my numbers off. This is about misdirection, right? Just making sure you're paying attention. Where is the slope?
the juncture is not really 1, it's infinity, right? So we can actually take any value between 0 to when the shift is there. So it goes this.
There's no, so you literally have to think of it as rotating, right? So the slope is undefined. How did you define the derivative? To answer your question, the way we define the derivative is how much does a small perturbation of the input perturb the output, correct? So suppose I have a function of this kind, and at this point, suppose I perturb the input in the negative direction. What is the output?
It's the same.
The output is 0, correct? If I perturb it in the positive direction, what happens? The output is the same as the perturbation itself. So if for a negative perturbation, you get a slope of 0, a derivative of 0. For a positive perturbation, you get a derivative of 1, right? That's why it's undefined. But if I think of it as rotating, then everything between 0 and 1 is valid. But there's no situation where a perturbation is going to give you an output that's greater than the perturbation itself. So it's between 0 and 1. Right? Okay, guys, somebody want to answer this question? We are way past the minute mark for this. This was easy. So anyone on Zoom, do you want to answer this question? 2, 4, and 5. So 2, 4, and 5, those are the ones that are right. Yeah. If I have max z1, z2, z3 computed at 1, 2, 3, then the derivative with respect to z1 is 0, with respect to z2 is 0, and the derivative with respect to z3 is 1, right? Yes?
But so when we say 0 to 1, is that 0 to 1 inclusive or 0 to 1 exclusive of 0 and 1? We have to pick
Inclusive, right? Because it is 0 and it does become 1, correct? And typically we use 0, but then you could use 1 and 2 just as fine. And the odds that you will hit that particular point during computation are essentially 0, so you don't have to worry about it, okay? So going back to our backward pass, all of these terms, these derivatives that we looked at, if your activation function is, if you're at some point where the activation function is not differentiable, then you could be using these subderivatives. Now, strictly speaking, subderivatives are only defined for convex functions, but the basic principle still holds, right? So, okay, so here's the overall approach. For each data instance, you're going to perform a forward pass where you pass the instance through the net, score all intermediate outputs for all the computation, and then you sweep back through the network and iteratively compute all derivatives with respect to weights. The actual loss is the average of the divergence over all the training instances, and the gradient is going to be the average of the gradients of the divergences for the individual training instances with respect to the parameters. That's what you're going to use in your gradient update rule, right? So this is just the complete back propagation approach, where you would first, if you're using gradient descent to train the network, then you would initialize all of your parameters, and then you go through all of your training instances, t equals 1 to t. For each of the training instances, you pass it through the network and compute the forward pass. Then you perform the backward pass and compute all the derivatives. You finally compute the average derivative over all the training instances and use those to update your parameters. And then go back and repeat the whole process. That's your training loop, right? And you do this until the loss is converged. Now, we have 7 minutes. So I'm going to take 7 minutes to introduce an idea, right? I've written everything in scalar form. We were speaking of scalar derivatives, right? And scalar variables, every variable dealt with by itself. In practical applications, you're not going to be doing this with scalars. If you've been working on your homework, you haven't written a single scalar equation, hopefully, right? Because if you did, your code is going to run forever for homework 1, P1, question 1. Now, we do this using matrices and vector notation and vector math and vector algorithms because A, the notation is simpler. B, where you have lots of really nice vector matrix libraries that make the operations much faster. So we are going to try to restate everything in vector form, and you'll find that all of those complicated looking equations become really trivial, right? To do this, first we're going to have to introduce some notation. So again, if you go here, look at these terms over here. These z's, which are the affine values at all the neurons of a layer, I can write them as a vector, top to bottom, as a k-dimensional vectors, or as a d-dimensional vector, where in this case the notation is changed slightly. The subscript represents the layer. So the z under subscript k represents the vector of affine values at the kth layer. Similarly, I can take all of the outputs of these activations and write these two as a vector. And so these guys over here, they are going to form this vector yk, which is the vector of the outputs of the neurons on the kth layer. So this notation may clear to you, right? It's just a vector way of representing the entire layer. And now every neuron in the layer has a bias, right? So now I'm actually going to explicitly represent the bias because it's simple enough in vector notation. And so I can represent all of the biases of the neurons as a vector. Now if I have d neurons in a layer, what is the dimensionality of z? Someone? Nivedita? If I have d neurons in a layer, what's the dimensionality of the corresponding z? D. And Namrata, what's the dimension of y? And what is the dimension of the bias? Also the same, right? But what about the weights coming into the layer? I can put the weights now as a matrix, right? So I'm going to write the weights, and the matrix is going to have as many rows as the number of neurons in the layer. Okay, so it has an analogy to the bias B. And the set of weights to the jth neuron are going to be the jth row of this matrix. So if you look at this weight matrix over here, if you look at the first row represents the set of all the weights coming into the first neuron in the layer. And which is why as you go through that, unlike standard matrix notation, you'll find it's the first index of the W term that's changing, not the second, because the second index is the destination neuron, right? And those are all the weights from the various neurons in the first layer in order, right? So is this making sense? Right, this notation? Okay. So once I write things in this notation, I can write something very simply, right? You can see that my battery has died. The affine vector at the kth layer is simply going to be the weights matrix for the kth layer, multiplying the output vector of the k minus 1th layer plus the bias at the kth layer. So you can see how much simpler this equation is, right? And so also, now I can say that the output of the kth layer is simply obtained by applying the activation of the kth layer to the affine vector at the kth layer. And we can check how this works. Like so. We can actually verify that this works because remember, our scalar equation was that for the kth layer, zi superscript k was summation I comma zj I comma j wi of k minus 1 times yi of k minus 1 times wij of k plus bj of k. This was the equation that we had when we were writing it in scalar form, correct? Now let's see whether this works out over here. It does. Consider the first. If I just take w times y, right? And let me call this 0 and 1 for just because I need something, right? If you work out the equation, that's going to be w1 1 y1 plus w2 1 y2 of the previous layer plus w3 1 y3 of the previous layer, going all the way till you get b1 for the first layer. So that's how that equation actually works out if you expand out the matrix multiplication. And comparing that to this equation over here, you can see that the two equations are the same, right? And so this is actually going to give you the actual output computations for the various layers. And then once you write things this way, I'm going to take one more minute just for this. Writing the forward pass becomes trivially simple. I can just set the input y0 to be the input, right? And then the first thing I would do is to compute the affine values at the first layer, which is just w1 times y0 plus b1, right? Then I can put those through an activation, f1 of z1, right? Then I can just compute the affine values at the next layer, put those through the activation, and go all the way to the end of the network, and then finally put it through the activation. So when I write the whole thing, now one of the things that you will note at the bottom is that I'm also explicitly indicating the fact that the network itself is a nested function. It's a nested function because you have each layer operates on the output of the previous layer, right? But then as far as the final code is concerned, the really ugly, complicated forward pass code that I wrote in scalar form becomes this very simple thing. I'm going to initialize my y0 to the input. Then I just go through the layers. At each layer, I first literally perform this affine computation to compute the, the summation goes over I, thank you. So to compute the affine vector, zk for the layer, and then I put it through the activation, and I'm done, right? So the entire forward pass, which is a big, ugly hunk of code, ends up looking like this. We'll stop right here, and I'll complete the rest of this portion at 7 o'clock.